Okay, class. I welcome you all to the 12th tutorial of the course Symmetry, Stereochemistry and Applications, which is conducted by NPTEL, whose course instructor is Professor Angshuman Roy Chaudhary from Aizen Mohali. I am Deepika, your PMRF teaching assistant. I am doing my PhD in chemistry at IIT Bombay. So, till now, we have conducted 11 tutorials related to the course Symmetry, Stereochemistry and Applications, along with one extra session. Okay, and in this today's last tutorial, we are going to discuss a few conceptual questions related to the last week's topic, which was crystallography. Okay, crystallographic symmetry. Okay, so let's move one by one through the questions. These are mostly theoretical questions. None of these are having any derivation. So, if you have understood the topic very clearly, you will easily get the answers. A crystal has a C3 axis along Z and three vertical mirror planes. Identify the point group. So, in this question, we have a crystal which is going to give us the same molecular structure if we rotate it by a C3 axis, which is nothing but rotating it by 120 degrees along the Z axis. Moreover, it has three vertical mirror planes, which, when we discussed mirror planes in our previous lecture about point groups, it is denoted by sigma v. Okay, so it has one C3 axis and three sigma v's. So, what will be the point group which will be associated to this given crystal? Okay, so to solve this question, we can approach it like this. Imagine holding a triangle shaped object. If you rotate it by 120 degree, it will look the same. And if you have a mirror, plane of mirror vertically, the mirror is going to bisect the side of the triangular object in such a way that both the sides will coincide. Okay. So, since we have three vertical mirror planes, the point group will be called as 3M. Okay, and the symmetry is will be called a balanced trigonal symmetry. We have another conceptual question here. We have a crystal with C4 principal axis along with one C2 three C2 axis perpendicular to it, and it does not have any mirror plane. Okay, so as you know, C4 principal axis, that means the principal axis will be a rotation by 90 degree. So identify the point group which will be having these symmetry operations. So the way the previous question we imagined a triangular box, this time you just have to imagine a square box. Okay, so the principal axis of symmetry is going to pass through this central point. Along with that, we have two C2 axis, and you can imagine the C2 axis passing through these two sides. Okay, so the crystal has only rotations and no mirror plane symmetry. So the point group which will be associated to this crystal will be called as 422. So the next question, Why does sigma h and Cn imply an improper axis? Identify the point group of the crystal which will be having these symmetry operations. So let us imagine that we are going to perform these two operations on a crystal, okay? Suppose we have performed a C4 operation on it. In that case, we are going to get this alignment of the molecular points. Okay. So the axis of symmetry, principal axis of symmetry, which is C4, is going to pass through this central point, and imagine it to be perpendicular to the plane of your screen. Okay. So let us just understand this using a molecule. Okay. So if we perform C2 over this molecule, it is like the C2 passing through here, which is on the plane, is going to rotated by C2. Okay. And we get this molecular arrangement. Now if we perform sigma H on it, which will be passing through the double bond, imagine it to be perpendicular to this C2 axis, we are going to get C here, T here, and B here, and A here. Okay, so we have performed C2 and sigma H together on this molecule, which is nothing but the improper axis of symmetry S2 on the molecule. Okay, thus the combination sigma H plus Cn will be the same as the improper axis of rotation S2. Also, the point group you have to write down will be Sn. Okay. Okay. So in the next question, you have to identify the point group of a molecule which is containing only inversion center. So to understand the inversion center, you can just relate to the previous question. It will be C2 C2 plus sigma H, which is also known as inversion. Okay, and in this particular question we have only inversion center present, no rotation or no mirror plane symmetry operation is present here. So the point group will be Ci, or you can donate it as -1 also. And the same example we can take the reference of in this question. We had talked about C2 and sigma H. These two operations in combination give us S2, and S2 is identical with inversion symmetry operation. So this example is going to have the point group Ci when we have Cn to be C2. Okay. Next question we have, discuss the symmetry of tetrahedron. So a regular tetrahedron has very high symmetry with 24 total symmetry operations, which we have already discussed in our previous classes. So if we count for the symmetry operations present in a tetrahedron, they will be four threefold axes of symmetry, which are C3 axis, which basically mean the rotation of the molecule by 120 degrees. And apart from that, we have three two-fold axes. That means three C2 axes. And when it comes to mirror planes, we have six sigma d planes present in a tetrahedron molecule. And apart from that, three improper axes of rotation are also present in a tetrahedron molecule, which will be S4. Okay, that means you must remember that a tetrahedron does not itself contain C4 or sigma H, but it contains combinations of C4 and sigma H to give us three improper axes of rotation. Thus, in total, we have 24 symmetry operations present in the symmetry group. And the point group is called TD for tetrahedron. Okay, it is actually written as This one. So in the next question, we have discussed the point group 6mm. So from the point group given 6mm, we have to conclude that the principal axis of the molecule will be C6. Okay. Along with that, it will have six vertical mirror planes, which will give rise to mm. So these operations which are contained in the 6mm point group, these are characteristic for a hexagonal symmetry. Okay, somewhat like if we draw it, it will look like this, where it will have six-fold axis of rotation. We have one C6, six vertical mirror planes, and C2 axis. So this is how 6mm will be described. Okay, the next question is again one theoretical question. Why is C1 valid? So first let's know what is C1. C1 represents identity operation. It is the lowest possible molecular symmetry containing only the identity operation. Okay, and molecules which will be containing C1 point group, they do not have any symmetry elements, no axis of rotation, no reflection planes, and no center of inversion. And if you are asked to give an example, we can write substituted methane of this type. So this particular molecule will not have any symmetry element present in it, and the only symmetry element it will have is identity, which is denoted by E. So the point group which will be associated to such molecule will be C1, and even absence of symmetry is a valid classification in point group. And C1 is equivalent to the identity operation, which is like rotating the molecule by 360 degree, which will basically give us the identical molecule. So the next question says describe P21C point group. Okay, so P21C is a space group which is common to monoclinic space groups. And if we try to understand the denotions, P is going to come for a primitive lattice which is monoclinic here. Okay, and 2 1 is going to denote a screw axis, which is a symmetry element combining rotation around an axis with translation parallel to the same axis, which kind of forms a helical pattern. Okay, and C here is going to denote a glide plane, which is a symmetry element combining a mirror plane with a translation parallel to that plane by a fraction of unit cell dimension. And it is a non-symmetric point group. This is how you can Describe a P21C point group. Okay. So in the next question, you have to identify the point group of a crystal which is having the symmetry elements C2 and sigma H. So here, although it is written as combination, interpret as C2 and sigma H independently. Okay. So let us understand this with an example. We have trans 1,2 dichloroethene here, and this is going to have a C2 axis of symmetry along with sigma h plane, which will be perpendicular to the C2 axis of symmetry, and C2 is going to pass through this midpoint, which will be perpendicular to the plane of the screen. So the point group which these molecules contain is C2H. It is actually written as C2H. So next question is one theoretical question. Differentiate symorphic versus non-symorphic. So the point groups which contain only rotation and translation, those are known as symorphic. So, symmorphic point groups contain rotations, reflections, or inversions, and they all have a common point fixed. Whereas the non-symmorphic point groups include glide planes and skew axes involving fractional lattice translations where no single point is fixed. Okay, we have already discussed screw axis on and glide planes. So symmorphic point groups do not contain these symmetry operations. And here we have given examples as well. PMMM will be an example of symmorphic point group, and whereas P21C will be a non-symmorphic point group. So in the next question, we have to identify the point group of a crystal having 4 C3 operations and 3 C4 axes of symmetry. So the symmetry point group which will be associated to it is basically written as M3M. So it actually represents the highest symmetry point group in the cubic crystal system, which is also known as full octahedral group. And here the first M refers to mirror planes perpendicular to the principal axis, and it has three such axes. Okay, and the second position 3 3 bar indicates The object is rotated by 120 degree and then inverted through the center. These four axes run along the four body diagonals of the cube. And the third position M refers to diagonal mirror planes passing between the axes, and there are six such diagonal planes. Okay, so this is why the point group associated is called M3 bar M. It has an order of 48, which means there are 48 unique operations that leave the object unchanged. And if we talk about the rotation axis which are contained in this point group, those are three four-fold axis and four three-fold axis along with six two-fold axis. And there are nine mirror planes, out of which six are diagonal, and it also contains inversion center of symmetry. Okay, I hope this is clear to you. So the next question is why five-fold is forbidden. So actually, in traditional crystallography, five-fold symmetry is forbidden because shapes with five-fold, like pentagons, cannot tile a 2D or 3D plane seamlessly. According to crystallographic restriction theorem, only 2, 3, 4, and 6-fold rotational symmetries can create repeating. Okay, so five-fold symmetry is forbidden because it breaks translational symmetry. If you try to tile a floor with regular pentagons, you will always have gaps. Okay, whereas square or hexagons fit together perfectly. So, five-fold symmetry will not have a periodic tiling. So, for this reason, five-fold is forbidden in crystallography. In the next question, identify the point group of square planar molecule. So, the primary point group for square planar molecule is D4H. It is characterized by high symmetry by the presence of principal C4 axis and four perpendicular C2 axis. Also, it has horizontal mirror plane and vertical mirror plane, sigma h and sigma v, and it also has inversion symmetry. Thus, the point group given to the square planar molecule is D4H. Identify the point group with C3 only. So the molecules which will contain only one C3 rotational axis, which is defined as the principal Z axis, it will be given the point group C3. It will have no mirrors or no inversion, and the order of the group will be 3. Okay, because the point group will contain operations C3, which is 120 degree, and C3 2, which is 240 degrees, and the identity operation. So these will be the symmetry operations contained in the C3 point group. Describe the point group F3MM. So F FM3M will be representing a molecule which will be face centered, and the M3M is denoting a cubic symmetry. It belongs to M3 bar M, or also known as octahedral OH point group. It is centrosymmetric, face centered cubic, and typically it represents high symmetry structures like sodium chloride, and it is the highest in the cubic system. So F basically is representing the lattice type. So in the next question, identify the point group with MMM. So MMM is actually the highest symmetry, centrosymmetric point group in the orthorhombic crystal system. The lattice type is orthorhombic. It has three mirror plane, one sigma h and two sigma v, and it has three two-fold rotation axes. Along with that, it contains one inversion center. We can take example of ethylene or naphthalene, which contain such MMM point group. In the next question, identify the point group with C2 and two perpendicular mirror planes. So let us understand this point group by an example. There will be one C2 axis of symmetry and two sigma v planes of symmetry, which will be containing the C2 axis. Hence, the point group is C2V. Next, we have describe P63MMC. So, here P is denoting a primitive unit cell and 63 is denoting a screw axis along the C axis. M will denote mirror plane and C is going to denote glide. So the symbol signifies a primitive lattice, a six-fold screw axis, a mirror plane and a C glide plane. It describes the structure with packed, staggered layers along the C axis, frequently found in transition metal, carbides or nitrides. And it is highly symmetric hexagonal crystal system characterized by a primitive lattice P. Okay. In the next question, identify the point group with C3 and sigma H. So I hope it will be now easier for you to solve this question. You have to just take an example the way we took in C2V. For instance, we can take example of boric acid. So the C3 will be passing through the midpoint perpendicular to the plane of the screen, and it will have sigma h, which will contain all these atoms. So it is characterized by a principal threefold rotation axis and a horizontal mirror plane. In the next question, identify the point group with three perpendicular C2 axes. So three mutually perpendicular C2 axes will have the point group 2, 2, 2. It is a crystallographic point group within the orthorhombic crystal system characterized by three mutually perpendicular two-fold rotation axes. And if we have to draw it, you can imagine a molecule of this type. So this will have a 2, 2, 2 point group. I hope this is clear to you. Okay, so with this we have solved the conceptual and theoretical questions related to this week's topic, symmetry, stereochemistry and applications, having questions from crystallographic symmetry. Okay, thank you very much for joining, and I hope with this you had an idea on the course Symmetry, Stereochemistry and Applications, since today's was the last live session conducted for the course. Okay, and all the best with your studies. If you have any queries, you can post it on the YouTube channel, or you can also approach through my mail ID. Thank you very much.